session. So yeah, so this week I'll probably cover week 9. So let's first try to go over the material. Probably we'll go over the questions there. So yeah, let's get started. Just 1 second. Yeah, hello. Yeah, so can you see the screen? Okay, can everyone see the screen? Okay. You. Okay. Let's get started. Yeah. So this week, like, they will be covering Bayesian networks. So Bayesian networks are a type of probabilistic graphical model that uses Bayesian inference for probability computations. So Bayesian networks aim to model the condition dependence of one event on the other. So here is an example. So let's say it's a cloudy is one of the variable. Then if it's cloudy, do we need sprinkler or not? That is the other variable. Then the other thing is the rain. That is, rain can be true or false. And then then the final variable is wet grass. So this cloudy variable can be true and false. Based on how the cloudy variable is, that is this true and false, because the sprinkler can be true or sprinkler can be false, right? So in here, the cloudy variable is false, then you can either use a sprinkler or not use a sprinkler, right? But if the cloudy weather is true, you can reduce the probability of using the sprinkler, and like you can make the sprinkler probability become more false. So this is how what are Bayesian networks. Okay. Okay. So these are Bayesian networks. So they have this property that is like a node is conditionally independent of its descendants given its parents, right? So given its non-descendants, given its parents. So if I specify the parents of the nodes, right? If I specify the probability of the parents, you can actually get the probability of the child, right? And you don't need any other information about any other node except the probability of this. Okay, so okay. So so yeah, so a node is conditionally independent of its non-descendant when it's present. So in the above example, let's say if I want to calculate the probability of the event of using a sprinkler given cloudy and rainy variable, it will be just P of sprinkler given cloudy because this rain variable is independent of the sprinkler. So to determine the probability of sprinkler, you only need its parent, that is cloudy, right? So this is the Markov property that Bayesian networks satisfy. That is that it is conditionally independent of its non-descendants given its parents. So here, let's say if I want to calculate this probability, P of AC, the joint probability of AC given B, that would be P of A given B multiplied by P of C given B. And then the probability of A A union B union C. So that would be probability of A given B, probability of C given B, because we only need the parent probability and the probability of B, right? Because this is an independent variable in itself. Okay, so this is how you decompose the probabilities in a Bayesian network. So please feel free to unmute yourself and ask any doubt if you have, because I cannot monitor the chat. So please feel free to interrupt in between. So in real world, let's say if we want to model the task of a task of modeling a student's marks for a given exam. So what are the variables that can be there? That can be exam level, it can be IQ level, then there are this variable called marks, and there is this variable called admission, then there is this variable called aptitude score, right? So in the exam level, you can have two variables, that is E0 and E1, and in the IQ level also you can have two variants, that is I0 and I1, right? And based on these like different combinations, there can be 4 combinations in the marks, that is that I0 E0, I0 E1, I1 E0, and I1 E1, that it comes into marks. Then there is aptitude score, that's variable, that's a function of this IQ level, and then there is admission. Okay, so these are all the probabilities which are given. Okay, so let us say, like, I want to model the probability of a certain like certain event, right, which specifies what is the value of A, what is the value of M, which is the value of I, what is the value of E, and what is the value of S, right? So if I want to write this, is what I will do is I'll just like write the probability of the variable and condition on its parent, right? So A is conditioned on marks, M is conditioned on IQ level and the exam level, the S is conditioned on I, and then this PI and PE, they are the free variables. Okay. Now calculate the probability that in spite of the exam level being difficult, the student having a low IQ level and a low aptitude score manages to pass the exam and secure admission to the university, right? So this we want. Uh, uh, so we want to do that. Okay. So 0 means low and 1 means high. Okay. So this event that is there in this this corresponds to having a, that is like low aptitude score, that is A equal to okay. So admission equals A is a variable that defines admission. Okay, and then there is this M variable that determines the marks. Then there are I and E variables that determine the IQ and the exam level. And then the I is the IQ level and the exam level is E. Right. So what they're saying is P of A equal to 1. That is he gets the admission, and he has a low aptitude score, that is this S is 0. Then low IQ level also, that is I is also 0. Then difficult exam is so E equal to 1, and he gets yeah, he is able to pass the exam, so marks would be 1, so M equal to 1. So this is like, if we decompose this, we want this. Okay. So what we will do is we will actually like initialize the values like what we want. So we want this P of I equal to 0, P of equal to 1, S equal to 0, I equal to 0, right? So we can decompose this in this form, and we will actually put the values of all these variables, right? So all these variable values are given in this table, right? That is this. So let's say, for example, P of I equal to 0 is 0.8 here. Okay. P of A equal to 1 is A equal to 1 given M equal to 1 is 0.1. So we'll do that. So the first one is 0.1. P of this E equal to I equal to 0 was 0.8, P of equal to 1 was 0.3, P of S equal to 0 given I equal to 0 is this, S equal to 0 given I equal to 0 was 0.75, right, and then there is this 0.1 of this P of M equal to 1. Okay, so this will be the final probability that you will get for this particular event. That is, calculate the probability that in spite of a score level being difficult, the student having a low IQ level and low aptitude score managed to pass the exam. Okay. Okay. Then yeah, so there can be further real life examples which can be modeled in such a way, right? So like let's say Pearl lives in Los Angeles. It is a high crime area. Pearl installed a burglar alarm. He asked his neighbors John and Mary to call him if they hear the alarm. This way he can come home if there is a burglary. Los Angeles is also earthquake prone, and alarm goes off when there is an earthquake, right? So burglary implies that there is an alarm, and earthquake implies that there is also an alarm, and if there is an alarm then John calls, and if there is further an alarm then Mary also calls. So these can be the following event, and this can be modeled in the same way we did above. You can model all these in terms of probability. Yeah. So this is one more example that like how it is. Yeah. So one other thing is that you have this something called conditional independence. So conditional independence means that these two variables, they are not independent, right? These toothache and catch, right? But when you condition them on cavity, they are independent. So P of toothache and catch conditioned on cavity is equal to P of toothache given cavity multiplied by P of catch given cavity, right? So they are conditionally independent. Yeah. Now the thing that could be a like something that is like sampling from the distribution, right? How can you sample from this distribution, right? So sampling means that you actually draw something out of the distribution. So for example, samples people greater than 60 years age in New Delhi, right? So like how you can get is that you can see in your computer science class, you can call on landline, call on cell phone, check Facebook, count election booth. So all these variables are related to this. Like they can determine if the people are greater than 60 years age in Delhi. How many, like what's the probability of this event, right? This way, these events are there, right? So then the other concept is called rejection sampling. So you sample you sample from the prior, right? The prior knowledge you have. If you reject the sample if it does not match the evidence, okay? So it returns consistent posterior estimates, and it is like expensive if this P of E is small, that is the prior of event is small. So P of E drops off exponentially with number of evidence variables, because if there are a lot of evidence variables, then this PE will be small, right? So this PE is evidence. Yeah. So oh, the thing that now we want to do is we want to estimate. Let's say we have made one model, right? We have made one model that this particular event is linked to other event in some or the other way, right? In a probabilistic graphical model, right? That we had this graph. So now we want to estimate the parameters of this model, right? So by estimating the parameters, what we mean is that we want to determine the probabilities for each of the event condition on that of their parent, right? So what we actually do is we can actually do this thing called counting, right? So in counting, you count all the events which are having these particular variables, that is E equal to 0, earthquake being 0, B equal to 0, and A equal to 0, right? And they can be 1,000. And then P of 0, comma 0, comma 1, and this, right? That can be 10. And then what you do is you actually create a table of this. And after creating the table, you can calculate the probabilities of each event based on the whatever counts you had. Okay, so yeah, so what happens is in this, what the issue becomes is that the probability in some cases can be, let's say, 1, because like you can only you only, let's say, uh, have observed certain event happening for only a certain amount of time, right? You have not observed for a long time, right? So let's say if you want to think about something like possibility of happening a burglary in your house, right? So in that case, the probability of that event is very small, right? So if you just count, let's say I'm living here for 10 years and there is no burglary, and you can say that, okay, counting all the days, and you might say that, okay, like the probability of having a burglary in this area is almost 0, right? But that's not true, right? So let's say like uh, it stumps the gift sampling, and low probability states become impossible. Okay, so what can be the solution for this, improving this probability of this rare events, right? So the solution is smoothing. So why, like, we want to deal with the events observed 0 times, that is that event particular n-gram. And so how we can do this is we shave a little bit of probability mass from higher counts and pile it instead of 0 counts for the rare events. We can use something called Laplace smoothing or advanced smoothing, that assume each event was observed at least once and add one frequency to all the frequency counts. Right. Yeah. So yeah, like the other thing that could be there is that this counting with smoothing. So in this all these cases, like you add one to all the counts you have. So this is the example of advanced smoothing. Okay. Okay. So whatever we did currently, right? The thing that we did, right? Find parameters. We are trying to use this method of counting, right? And based on the counting, we were determining like what event is likely, right? So what we are actually doing here is that we are trying to find parameters that maximize the probability of seeing the data, that is D, and given the parameters theta. So this is argmax of theta over theta and P of D given theta, right? And it's easy to compute. It's like just uniform, like it just requires you to count. It assumes that there is a uniform prior. That is like we don't have any special knowledge about any other extra events that we have not seen. So whatever we have counted is the knowledge we have. So okay. So any doubts till now? Anyone has? Hello. I'm audible, right? Can anyone confirm? Hello. Yeah, thank you. Yeah, so this is called the maximum likelihood. That is like you're trying to get the probabilities based on the counts for each of the events, right? And it assumes like uniform prior. Okay. So like so what does prior mean? So prior is your belief before seeing the data that okay, like how much likely is that event before seeing any data, right? So if you assume uniform prior, that means that all parameters are equally likely. So that was what was happening in the ML estimate, right? So then what the other estimate is, it's called MAP, that is maximum a priori estimate. We want to maximize probability of parameters after seeing the data. That is like P of theta given data. And if you know Bayes rule, like you can convert it into P of d given theta into P theta divided by PD. So PD is actually independent of theta, so you can remove that term. So this means that argmax of P of data given theta multiplied by this P of theta, the prior knowledge that we have, right? So this is how you can incorporate the prior knowledge that you have into the framework. Yeah. So allows user to put additional domain knowledge and better parameters when data is sparse, and reduces to maximum likelihood when you have infinite data. Yeah. So let's do one example first, then probably move to the question. Okay. So what is called a full Bayesian learning, right? So view learning is Bayesian updating of probability distribution over hypothesis space, right? So H is the hypothesis variable, and it has values H1, H2, and Hn, and prior pH. And the jth observation dj gives the outcome random variable dj, training data d equal to d1 dot 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 dn. Given the data so far, we want to each hypothesis has a posterior probability, that is P of hi given d, that is alpha times P of d given hi and P of hi. And P of d given hi is called the likelihood. Okay. So predictions use a likelihood weighted average over the hypothesis. That is this, right? So the good thing here is that you don't have to pick any hypothesis right here, because you are averaging over all hypotheses. So here, like in the earlier sense, you are averaging over all the variables that are possible, right? So this is how uh, this full Bayesian learning works. So H is the hypothesis variable that has H1, H2 values and a prior pH. Jth observation, that is dj, gives the outcome of the random variable dj. You have a training data, that is d1 equal to dn. So given data, like what is the probability of a particular hypothesis being true, that is given by this, right? And what finally you want is you want to calculate this probability of x, and that is a particular event happening, and in that particular event you also have certain amount of data, right? So what you do is you actually try out all the hypotheses, the possibilities that hypothesis can take, that is hi can be 1, 2, 3, and you actually aggregate it. So you don't need to pick any best hypothesis that would have been true on this data. You can actually do all of it. So this is very important example. So let's see here. So suppose there are 5 kinds of bags of candies. 10% are H1, 100% are cherry candies, 20% are H275 are cherry candies, plus 25% are lime candies, and 40% are S3, 50% cherry candies plus 50% lime candies, right? So these are the 5 kinds of bags that are there, and then we observe that okay, like we randomly choose a bag and then try to get out the candies from that bag, right? And what we observe is this, like all green candies we observe. So what kind of bag is it, right? That is like what is the hypothesis, right? Like we have drawn it from one of the bag. So this process is called learning, right? That means that you are trying to predict the probability of the hypothesis. And what flavor will the next candy be? That's the problem of inference, right? You have now assumed that okay, like one of the hypothesis was true, and after assuming that hypothesis was true, so now you want to say that what flavor the next candy will be. So here is the plot that you have. So the posterior probability of having an hypothesis H1 given this data that we had, that all candies are this. right? So what you can say is that if number of samples, let's say, happens to be in D is that uh, data is, let's say, very like if it was 0, then it was almost like the prior that we had here, that is this one, right? But as we keep on observing things, things change. So when there is one green candy, so the probability of this particular bag goes to 0, right? Because this particular bag has no green candy, right? So this particular bag goes 0, and all the like the earlier ones that are there which have less number of green candies become 0, right? So it starts going from here to 0, that is the green curve also goes to 0. And then the probability of seeing that, okay, like it being the last bag, right, which has all green candies, starts increasing, right? Because uh, as you see more and more data, you keep on refining your hypothesis, right? Okay, so then yeah, so then there's one more example that is like so that was an example of learning, right? You are trying to learn the hypothesis, right? Which of the hypothesis is probable with the given data that I'm observing, right? So this is the hypothesis, right? Then the other thing that's there is that you want to also think about learning, right? So, okay, so let's say you are seeing this example that is 0, 1, 0, 1, 0, 0, 1, 1, 1, and now you want to know that, okay, what's the probability if A and C are 1, and what's the probability of what could be here, that is B, right? So what you do here is that you initialize with whatever probabilities you have, then you calculate this expectation, and then based on data you calculate expectation maximization, and then in the end you see that, okay, how the probability is, right? So this process is called expectation maximization. It is very important process in the Bayesian learning community. Okay, so what you do is you guess probability for nodes with missing values and compute the probability distribution over the missing values given our guess, and update the probability based on the guess value. This you repeat this until convergence, and this is guaranteed to converge to local optimum. So what I would say is that this particular topic is very important. So please take a careful look at expectation maximization. This is very important topic. But yeah, this week it was just covered a bit. So we'll cover this a bit in the next week as well. Okay. So now let's have some questions. Okay. So which of the following are about Bayesian network? So in these questions, like if you have any doubt, please unmute yourself and just ask. So we want to see this. This is the graphical model that we have. So we want to see that which of the following are true about the given Bayesian network. That means that this C. So C has its parents, that is A and B, right? So C probability of C only depends on A and B, right? So C is conditionally independent of D given A, right? So if I even put D right here, because it's if you are given A, right, the A is influencing this, so this will be independent, right? Because C is being only influenced by A, and if I specify A, they become independent, right? Because A is only influencing them. And then the other point is that C is conditionally independent of D given E, right? So C is independent of D given E, right? So if I give E, right, so I have to calculate the probability of C given D and E, right? So, but they actually are not the direct parents, right? So if they are not the direct parents, we cannot make an inference about the probability, right? So only thing that you have to keep in mind is that the only independence you can do is with respect to the parents. Okay. Now that B is conditionally independent of A, so given C, right? So B is conditionally independent of A given C. So B is an independent variable, so I want to calculate B given A and C, right? So how can I write this is that I can write this as P of B So wait, let me just try to let me just try to do a bit of whiteboarding. Just bear with me. Hello? Yes. Hello? Yeah. I'm there actually. I'm trying to do things on whiteboard so that you can understand better. Okay, can you see here? So can you see the whiteboard? No. So let's say if I want to find that, okay, uh, something is conditionally independent or not, right? So what I will have to do is that whatever the variables I want to like check with conditional independency, I'll calculate the joint probability of that. Let's say I want to calculate the conditional independence of A, B given C, right? So for conditional independence, what should happen is that this should be equal to P of A given C multiplied by P of B given C, right? Right. So these are the two things, and these are two are the important things, right? This is how you should decompose it. Okay. Now coming back to the question. So so now let's say if I want to do B and A given C, right? So I want to calculate the joint probability of B and A given C, right? So so I can write this. So P of B, E, so if I am given C, right, I cannot write that part as uh, P of A into P of B, right? Because this is not independent, right? And then the other thing is that P of and C, B and C given A, right? So if this B is conditionally independent of C given A, but actually it's influencing C, right? So this you cannot write. So, so this is the correct answer. So, so given C, D, and E, which of the following variables given C and D is independent of which of the following variables, right? So if we are given C and D and E also, right? So, oh, this is the probability of this particular part only, right? So if I've given C and D and I'm also given probability of E, right? I don't require the probability of A and B, right? Because I can determine the probability of E just based on solely on what are the value of B and C. I don't need any like probability of A and B. Right? So that's why like the answer is both A and B. right? So the thumb rule is that if you require something else from the top, you are not independent. If you don't require it, you are independent. So which of the following statements is true? So Bayesian network can be used to find the number of satisfying assignment for any Boolean formula. So, what you can do is you can actually make a tree of this thing and then try to find this in Bayesian inference, right? And inference in a Bayesian network always has exponential time color complexity irrespective of the structure. So it kind of depends on what the structure of the Bayesian network is, right? That means, let's say if you are something like a Markovian structure, right? This inference can be very fast, right? Because you only depend on the last variable, right? So that's why inference can be very fast in the Markovian network. And inference in a Bayesian network may be polynomial time. That means like if the things are Markovian, you can make it very fast, right? Because to calculate the probability of the next state, right? Next state, you only just depend on the previous state. And cut sets can simplify inference in Bayesian networks. That means that if there are sets which are cut from the different graphs, you can simplify inference in Bayesian network. Okay. So consider the following probability metrics. Each row contains a value of x and each column contains a value of y. What is the value of p of y given to given x is given to? Right. So we want to calculate y equal to 2, x equal to 2. So how we'll do it is we want to